All right. So here we are, the very last class. By the way, for graduate students, those of you who are also in 610 during a previous hour, I had an office hour in case anyone had questions about work in that class, and no one showed up. But after this class period is over, reviewing for a final, if any of you have things you want to ask about that after PDEs is over, then I can stick around for that too. But now we're going into the final. Okay, so my plan is to have a final posted in Canvas by Friday, this Friday. So then you would have a whole week to get it done. So I was waiting until after the review, just in case if the review leads me to edit something. But if the questions are all there, I just need to make sure that things are sufficiently clear, and then I'll get that out there. Okay, so alrighty. So we have 7 problems in total. The first 4 problems are old material. And actually, what I'll do with each problem, I'm going to indicate what lesson it's based on, so you know what part of a notes to look at. So, for instance, the first problem deals with lesson 9. So this is heat equation with non-homogeneous. We have a source term here. Boundary conditions are homogeneous, and then we have initial data. So lesson 9 was about eigenfunction expansions. So you would need to expand the initial data and the source term in the basis of eigenfunctions. And so the ODEs that you would be getting, well, first you're getting the eigenfunctions. The eigenfunctions stem from the boundary conditions. Now, in this solution, I went through all the steps, which is not something that I would expect you to do. Like here we have du dx is 0 at both ends. So we've seen from many problems, the eigenfunctions, therefore, are cosine of n pi x over L. In this case, L would be 1. So, and that's worked out here, how we get the eigenfunctions of cosine n pi x. So then you expand your source term and initial data in the basis of eigenfunctions, which is easy to do in this case because they're already a linear combination of eigenfunctions. So most of the f's and b's would be 0. So we're just picking out the ones that are non-zero. Your solution is also expanded in the basis of eigenfunctions with coefficients that depend on t. And that leads to these ODEs. So it's always going to be something of this form, where the appropriate eigenvalue goes here, your Fn goes here, and then Bn would be the initial value. Now, in what we see here is in most cases, Fn and Bn are both 0, so then the solution is 0. Otherwise, this solution formula applies, so you can just go ahead and directly use this. And in this particular problem, we have Fn is non-zero when n is 2. We have Bn is non-zero only when n is 1. So these are the solutions that we get that are non-zero, and then we multiply these by the corresponding eigenfunctions, so cosine pi x for n equal 1, and cosine 2 pi x for n equals 2, and add them together, and there's your solution. So this right here is your key. This is how you get your this formula right here, based on the coefficients of your initial data and source term in the basis of eigenfunctions. I should mention it's a little simpler in this case, just because Fn, each Fn is a constant. That's because the source term in this problem does not depend on t. If it does depend on t, we'd have Fn of s here, and then there'd be a bit more work involved in evaluating the integral. But here, Fn is a constant, so I just pull it out and then integrate this. So sorry, if this is a solution formula that always applies, if Fn's a constant too, then it goes directly to this. As I talk about each problem, please just go ahead and jump in if you have any questions about that problem.
So, in the case it's not dependent on t, is it like back to where we had that solution formula of how to find them?
Well, this is still the solution formula.
Okay.
Yeah, so this is one I gave in the lesson 9 notes. It's just that if this is not a constant, it has to stay in the integral. So, I mean, yeah, the solution formula was left as an integral because you never know what this is going to be.
Okay.
Yeah. And then here, actually, I want to take a look at something here. Whoops, wrong thing. Okay. That's because with source term not depending on t. And it will not depend on t in the test either. So then you'll be able to jump directly to here. Any other questions about this one? Okay. The next one is drawn from lesson 12. So here we have a Cauchy problem for the heat equation. So because the domain is the entire real number line. And then so you just have this initial condition. So then you would take the Fourier transform. This is table A, the table of Fourier transforms in the back of the textbook. So then your PDE, when Fourier transform, becomes this ODE. So then you go ahead and solve that. So what we have here is, okay, where to go? Well, what you need to do is take the transform of the initial condition that you're given using the table. So then, so this is a transform of the initial data. Okay. And oh, we have a typo here. Oh, okay. So this is your ODE for each Fourier coefficient of a solution with this initial value, and therefore this is the solution. So and all it is it's just the initial value times e to the minus omega squared t, and that's what we end up with here. And so then what you can do is then take the inverse transform, and that's your solution. And a problem will state, either the integral should be evaluated or the solution can be left in integral form. Okay, the next one is from lesson 20. So wave equation, but on a bounded interval, so separation of variables applies. So from a boundary conditions, you would determine your eigenfunction. So in this case, u instead of du dx is specified at the endpoints. So your eigenfunctions would be sine of n pi x over L, where L is equal to 1. And then you have your two initial conditions here. So your solution is going to have this form, where Cn and Dn are based on these initial conditions. Here are the formulas for Cn and Dn. Notice with Dn, because that corresponds to the initial condition on du dt. So we have this extra factor of L over Cn pi that we don't have here. Your initial condition on u goes here. Initial condition on du dt goes here. And then you see, okay, what are your C's and D's? So what happens in this case is this integral here is a Fourier sine coefficient of f of x. And in this problem, your initial condition on u is sine pi x. So you get C1 is equal to 1 and all over 0. For du dt, we have a coefficient of 1 when n is equal to 2. So what that means is when n is equal to 2, this integral, 2 over L onward, so everything except this factor out front, that would be equal to 1. And so I got that here. And then you have to multiply by this, and that's where 1 over 4 pi comes from. Little c is equal to 2 in this problem. And then you can construct the solution from there. Any questions on this one? The last problem, old material, this is from lesson 27. Method of characteristics for a linear PDE. So method of characteristics gives you these ODEs. So dxds is a coefficient of ux. dTds is a coefficient of ut. And then we have duds plus whatever term is left over on the left side is equal to the right-hand side, which is 0. So for x, the initial value is tau. For t, the initial value is 0 because our initial condition is specified on the x-axis. And then cosine, the initial data with x replaced by tau is the initial condition for this ODE. So then you go ahead and solve these ODEs. So with dx ds equal to s, x is equal to its own derivative. So it's the exponential e to the s times the initial value. T turns out to just be s because of this ODE initial condition, just by integrating with respect to s and applying the initial condition. And then finally, u would be equal to e to the minus 2s because of this coefficient here, times its initial value, that would be cosine tau. But then what has to happen in this case is, now here's your solution in terms of tau and s. You need to write s and tau in terms of x and t by going back to these solutions here. In this case, s is just t, which is often but not always how it turns out. And then here we can solve the equation x is equal to e to the t tau. We can solve this equation for tau and fill that in here. So you set up characteristic ODEs, solve those ODEs. One for U gives you a solution in terms of S and tau. Go back to your solutions for X and T to express your solution in terms of X and T. Everything else is on newer material. We have one problem from lesson 33, interior Dirshley problem. So Laplace's equation on a disk of radius 1. So U of 1 theta is equal to this boundary data. And for this problem, this is the general solution formula on a disk of radius capital R, which would be 1 in this case. And then you get the coefficients A and Bn based on the boundary data. But these are just the Fourier cosine and sine coefficients of your boundary data. So when the boundary data is expressed as linear combinations of these sines and cosines, then you can just get the coefficients A and Bn from the coefficients of that linear combination. And that's because in this case we have sine 3 theta, there are no cosines, so that's why B3 is equal to 1 and all other A's and B's are equal to 0. But once you have these coefficients, then all you're doing is you're putting in factors of R to the n. So that's why we get, so in front of sine 3 theta, you're just going to put an R cubed. So that's a quickest way to a solution when you have that kind of boundary data, is that in front of each term, you just put the appropriate non-negative power of R, whether it's sine or cosine. The same is true of problem 7. That's the exterior Dirshley problem. The only difference there is the you're putting negative powers of R in front of each term. So the last two problems are both from lesson 34. Here we have Dirshley problem in an annulus. So here's our inner boundary data, here's our outer boundary data. And the solution formula that applies in this case is this one. So this definitely takes more algebra, because what you're doing is you're solving system of equations 2 by 2, like system for A0, B0, and AN, BN, and then CN, DN. Based on the boundary data you have, most of these will turn out to be 0, just because in your system of equations, I'll show you here. There's a whole set of them. So for each, so what we have is you look at this system by itself, and then here these two for AN and BN, and then these two for CN and DN. When you have for each pair of equations, if both right-hand side values are 0, then the coefficients are 0. So we're looking at cases where in each 2 by 2 system, at least one of these right-hand side values is non-zero. Those are the ones you actually go to the trouble to solve. And first equation, you're plugging in your inner radius to the n minus n power. Second equation, you're taking your outer radius, raising that to the n for minus nth power. Oh, okay, so R2 is equal to 2. Okay, So G1 is sine, and G2 is cosine. Here you take advantage of orthogonality. The integrals of sine n theta or cosine n theta just by themselves are always 0. So we would get nothing from here. Here, with G1 being sine, this will only be non-zero when n is equal. Well, actually, this will always be 0 because sines are orthogonal to all cosines. This will be non-zero only when n is equal to 1. And because the coefficient of sine s here is just 1, then the value of this integral will be 1. Similar for G2 being cosine. So this will only be non-zero when n is 1. This will always be 0. So once you fill in the values of these integrals, so this system, everything is 0, so A0 and B0 will be 0. This will always be 0. But for the outer radius, we get 1 when n is equal to 1 and 0 otherwise. And then here with C and D, the first equation, we have right-hand side a value of 1 when n is 1, otherwise 0. So that means that A0, B0 are 0, An and Bn are 0 for n equal 2 onward, and Cn and Dn are 0 also for n equal 2 onward. So the only interesting system in this problem is when n is equal to 1. So for the first case, we have this system of equations, so you just go ahead and solve that, and you get 2/3 and minus 2/3. And then for this system, similar, but we have the opposite value being non-zero here. So we go ahead and solve that. What you get is minus 1/3 and 4/3. Okay. So I'm changing it from formatting here. Oh, okay. It's driving me nuts. There's always so much space at the bottom of these pages. Okay. So these are values of C1 and D1 that we get. So then we go ahead and substitute the values of our coefficients that we get into the general solution formula and get this. So the A's and B's go in front of cosines, C's and D's go in front of sines. Are there any questions on this one? This is a bit more of a pain. For these problems, a good idea to check your boundary conditions and make sure they're satisfied. Like if you plug in r equals 1 for the inner case, and then r equal 2 for the outer, and make sure that you really do get the G1 and G2 that were given. And protect yourself against minor algebraic mistakes. The last one, exterior Dirshley problem. So here's your boundary data. This is a solution formula that applies in this case, but with the additional, boundary data being a linear combination of sines and cosines are also a constant function, then all you're doing is taking the appropriate powers of R. So for to the 0 power for the constant term, and the -2 power for this sine term. That's what we have here. So that ends up being your solution. It's just a boundary data with r to the -2 in front of this. Now, this is when the radius of your boundary is 1. If it's not 1, you have to take this into account. So this solution formula is meant for exterior Dirshley problem with any radius serving as a capital R serving as the boundary. So A's are your Fourier cosine coefficients of your boundary data, and then the BNs are your Fourier sine coefficients of the boundary data. So we've come to the end. So this is your last chance during class time for any questions about any of these things, or also about any ongoing homework you have. Remember, the lowest 2 are dropped, so I can save you some time.
Okay, I'm gonna have this reiterated. The powers for the R's come from, I get where the 0 power comes from for 1. Anything to the 0 is 1. But
Okay.
for sine, is it because of the argument?
Yes.
Okay.
Yes. So actually, let's go back to the solution formula. Yeah. So we have cosine or sine and theta, either one. You get an R to the minus n in front.
Okay.
And it's similar for the interior Dirshley problem where it's R to the plus n in front.
All right. Thank you.
Mm-hmm. Oh, this is wrong. It should be U of R. R should be the first argument. Dang it. And theta. Well, at least I've had a chance to fix some typos during this class. Okay, oh quiet ones. This is why I can't wait to be. I guess one reason why I can't wait to be back to in person next semester. But although what I will do for my classes is for anyone who cannot be on campus or doesn't feel comfortable being on campus, that I would still I may be in a classroom at the board, but also running it through Teams.
Thank you, Dr. Lambers.
Sure. All right. I guess nobody has anything. Well, I'll stop the recording now. But anyone has questions, and like I said, anyone who also has 610 questions, if you're in 610, is a good time for that as well, since I don't have any meeting until 4 o'clock. Okay. It's been a semester.
Thank you, Dr. Lambers.
Yep.
Thank you, Dr. Lambers.
Thank you.